Sljedeće predavanje je voda kao rashladni fluid. Kolega Aleksandar Pachai s fabrike Sabroe iz Danske. Please take a floor.
Thank you, Mr. Chairman. Ladies and gentlemen, I'm very pleased to be here again. I'll just wait for magics. Thank you. Good, thanks. I want to talk a little bit about water as refrigerant. And not everything has to be boring, so I also took a few words about the safety issues with water. Water is a very natural fluid, yes, I know, but it's also very important to life. Everybody, most living organisms, they need water, as you probably know, including human beings. Water is available everywhere, but not all water is useful for us because we need unsalted water. Not saying that there has to be no salt at all, but we cannot drink seawater. We need sweet water with minerals. Otherwise, we will not live so long. But there's also other problems with water. Of course, there can be, it can be frozen to ice. We can fall down from the roof in your head, so be careful. We are going into the cold season now. Water can also include sharks. You have probably seen this horror films and all this. It can also be full of rocks that can make ships fall. As there was an Italian ship over not so many years ago. Water is also can be full of chemicals or algae or something which makes it difficult, and you cannot always see it. That's what is making water a little bit difficult to keep clean. And as a safety thing, water is also causing more people dying every year than any refrigerant has ever caused by drowning. Just to give a few points about water. But if we use it as a refrigerant, it has a lot of other properties which is very good. A lot of you have learned a lot about water, probably during studies and all this. We know that the evaporating heat of water is about 2,256 or 57 kilojoule per kilogram. It is twice as much as ammonia, so they could indicate very low flows. So, but there's no need to go as low as 18 grams per kilowatt because it's quite a safe refrigerant. The atmospheric boiling point, let's get it done. Thank you. And the molar weight is very low, which means that you have to find other compressors, at least for air conditioning. We cannot use the normal turbo compressors because the molar weight is too low. So you need an axial compressor instead of a radial compressor. When it goes up in temperature, water changes a lot of property and the molecule becomes heavier, and it allows to use radial compressors at, say, 60 degrees and above. We will see that in a moment. The big problem with water is, especially at the low temperatures, it is in deep vacuum, 0.006 bars, so we are close to the triple point. If we go to, for example, minus 6-degree water, it is a difficult task to have. As you also know, water boils at 100 degrees at atmospheric pressure, so it's good as a heat pump fluid, and we are looking at heat pumps for 130 to 180 degrees C at the moment. This is just to show you a little bit about the pressure. You can see until 100 degrees, it's more or less flat along the 0 bar line because I have a problem with showing lower than that. But it is very low pressures we are talking about, and it is a challenge. And there, the axial compressor is actually a very good compressor to do this, and we have I will show in a moment a field test going on at the moment. What is also interesting is you can see here that when we get up in temperatures, you can see that the density of the vapor increases. And if we go into, say, vapor volume, you can see the vapor volume drops dramatically when you go past something like 70 degrees. Just to make a few extra comparisons here, you have the second row. It is the pressure, and you can see 0.006 bar at about the triple point, and 6 degrees is not much higher. But when we get up to, for example, 130 bars, we are at the phenomenal pressure of 2.7 bar. It is over so it will be covered by the PED. But as long as we are down in normal air conditioning area, we are not covered by PED, which is a cost reduction. Very interesting, where everything else will be with some cost issues when we go in PED. But you can also see the volume, cubic meters per kilo. It drops dramatically when we get up in temperatures. So there's a lot of potential for heat pumps. Here you see a picture to the left, which is the axial compressor. It can have multiple stages. It depends all on how much temperature lift you need. In some cases, you might even need a two-stage system. The compressor in test here, you can see the compressor is the small part and the diffuser is actually the big part. And the picture to the far right shows the boiling, but actually the boiling happens inside in a falling film thing, a little bit like this, where the water falls down, and about 1% evaporates to cool down the rest of the water. 1% means a lot of volume because of water vapor, but it's not very much water. The trick is also here, normally when you have a refrigeration system and a cooling tower, you always add water into the cooling tower. But in this case, you will have to add it on the low side of the system because you are evaporating and going out. And the open system here is the most efficient, but I have some numbers coming up in a moment. So you will throw out, but you can also close and make a dry cooler instead of the cooling tower, and then you have to recirculate the water back to the. But you will normally here accumulate all minerals in the water. You will accumulate that in the evaporator. So we will have to, if we are putting in the water here, we will have to clean it out now and then. Means that you have to break the vacuum and clean it. It's a technical challenge, but not a big one. The condenser water will come back here in this case as the water will be fully saturated with air. So the trick and the patterns around the whole technology here is about how to separate the air from the water, because if there gets too much air in, you cannot keep down the condensing pressure and you will lose all your efficiency. So that's the trick. Otherwise, you will spend a lot of money on vacuum pumps. So we have here some data for the first field test unit. It's a little bit smaller than the one we installed in 1996 at the same place. But the compressor have been shrinking from 4 meters in diameter to about 70 centimeter. So but we are running a little bit faster, and the impellers are fixed on the impeller. It was not the case in the old one from '96, where the impellers were sitting loose and they were just pulled around. And after a striking of lightning, the inverters were zeroed, so they started up in 0.2 seconds full speed, and the impellers fell off. This will not happen here. You can see also this EER, or the COP if you want. It is here given to 5.3 in round figures. Just to see the difference here. if we close the condenser so it becomes a dry cooler, and the evaporator has an extra, what do you call it, the COP will fall a little bit, but still, compared to our propane chillers, the water vapor is still a good solution, and the efficiency is very good and much better than the compressor we used in '96, which was a two-stage thing. And here we have the possibilities for making 13, 18 degrees with evaporator either as a closed loop with an extra heat exchanger between, or the condenser, the same dry cooler or open, and you can see that the COPs will be affected with the extra heat exchanger. But it has, of course, other benefits. And in the field test system now, because the water that we take in from the bore is full of iron, in this process we are cooling, don't like minerals in the water, we have to have this additional closed loop water for the machinery, and then we have closed the evaporator, so it becomes a closed circuit. We are also looking at the future possibilities for the same technology. Here you have a two-stage or a cascade system where we use seawater. We generate dry ice, or what you call it, slush ice, ice slurry it's called, where we evaporate water and then we go into the condenser, and this condensing heat is then put in as a load on the ammonia compressor, and then this is condensed out against a district heating system. The water vapor compressor, the water is then condensed and sent out back, but it is actually desalinated water. And in countries where you don't have, what I call it, fresh water or desalinated water in the underground, this is a technology that could be of interest for this also, where you can be making cooling at the same time as you are desalinating water for potable water. This is just one of the options you have. This ends my short presentation about water as refrigerant, and I hope that it has interested you. Thank you for your attention.
Thank you, dear colleague. Zahvaljujemo kolegi Pačaju.